Question 41. A key chemical characteristic of fuel cells is that the overall reaction is the same as the combustion reaction of the fuel which is used in the cell. Part A, write a balanced equation for the combustion of methane. Okay, so all it wants you to do is write down a balanced equation for what happens when methane undergoes combustion. So we have methane, which is CH4. Okay, and that's a gas. Okay, in combustion, it will react with oxygen. Okay, oxygen gas. And combustion always forms, presume it's complete combustion, carbon dioxide. Okay, and water. Let's put states for those. Okay, so the first thing when balancing combustion equations, start with the carbon first and go from there. Okay, so we've got one carbon. Okay, so that's balanced. Next, let's balance hydrogens. So we've got 4, 2, now we've got 2. So 2 hydrogen, 2 times 2, 4, and 4 hydrogen. Now I've got 2 oxygen, 2, 4 oxygen. So if I put a 2 here, I can write that with my pen. So 2, yep, okay. And that is balanced. Okay. Next question. What is the main energy transformation occurring in an operating cell? So in a fuel cell, the main energy transformation occurring is direct conversion of chemical energy to electrical energy. C. Why are fuel cells more efficient than conventional chemical fuel-fired power stations? So if you remember, a fuel cell is we are going directly from chemical energy to electrical energy, whereas in a fuel-fired power station, we have got lots more stages. So we're going from chemical energy to kinetic to mechanical and so on to electrical. And along that way, we are losing energy as heat. Whereas when it's direct from chemical to electrical, we don't have such a significant heat loss. Next part of the question. Okay, lots of information here. So types of fuel cells are usually characterized by the electrolyte, temperature of operation, transported ion, and fuel. Solid oxide, okay, fuel cells, okay, so it means it's going to be solid fuel, can run a variety of fuels, including diesel or natural gas. Okay, so natural gas, methane. They bring in oxygen from the air, okay, to be reduced at the cathode. Okay, so that's telling me that in this fuel cell, we've got oxygen coming in at the cathode and it's being reduced. And then past the oxygen, the oxide ions, okay, so that's the oxygen that's being reduced through a solid oxide electrolyte membrane to the anode, where the fuel is oxidized to produce electrons that are drawn out of the device. Okay, their high operating temperatures are dictated by the fact that the ions move more quickly through the electrolyte at higher temperatures. Okay, so assuming the fuel used in the standard solid oxide fuel cell is methane, write balanced half equations for the reaction at the negative electrode. Okay, so that's my anode. So it told me before that, you know what, I might actually I'll do the positive electrode first. Okay, so it told me at the beginning that it brought in oxygen from the air to be reduced at the cathode. Okay, so I know that my oxygen gas is coming in. Okay, and it is going to be reduced to minus to my oxide ions. Okay. I can't write now. Right. Okay. So then if we need to balance out the electrons, this will have gained, it's got 4 negatives, so it's gained 4 electrons. Okay. That is my reaction at my cathode. Okay, so then it's saying those oxide ions through a solid move to the anode where the fuel is oxidized to produce electrons. Okay, so I've got my fuel which was my methane. Okay, it told me that in the information. And it's reacting with these oxide ions here. Okay, so I'll add those in. Two minus. Okay, and I should be looking for it, shouldn't it? My bad writing. Okay, so it's reacting with my oxide ions. Okay, and if we go back to the beginning of the question, it says that the overall reaction is the same as the combustion. Okay, so that tells me that my products are going to have to be carbon dioxide and water. Okay, so I've got CO2 plus water. Okay, so yeah. Let's use those states. Okay, so they're my products. Okay, so I've got my CH4. Okay, so now I need to balance it. So I've got one carbon, that's right. I've got two. Oh, okay, so if I put a 4 here, okay, and then I'm going to have to got 4 hydrogen, 2 there. Okay, so that's my key elements balanced. Then I need to balance my electrons, so oxidation, so it's the last electron. So I've got overall 8 negative here, so I'm going to have to add 8 electrons this side to balance that out. Okay, so they're my two half equations. And most of that you have to pick out from the information that you're given. Question E, why could the operating voltage of a solid oxide fuel cell not be accurately be predicted from a standard electrochemical series? So if remember, the standard electrochemical series that is in your data booklets is done at 25 degrees. Whereas if we read the information here, it tells us that this is occurring between 500 to 1000 degrees Celsius. Okay, so it can't be accurately predicted from the standard electrochemical series, which was done under standard lab conditions. Next part of the question. Another type of fuel cell is the polymer electrolyte membrane fuel cell. This fuel cell uses hydrogen as its fuel, operates between 20 degrees and 80 degrees, and the membrane only allows the conduction of cations. So I need to write the half equations for the reaction occurring at the anode and the cathode. So if we remember when we had a hydrogen fuel cell, at the anode we have a hydrogen gas is being oxidized to form our hydrogen ions. And it's losing the 2 electrons. Okay, remember those 2 electrons will go through the wire, they will undergo, or the oxygen will undergo reduction, forming the oxide ions, which will then react with our hydrogen ions. So at our cathode we have our oxygen gas, which is reacting with our hydrogen ions. It's so bad writing. Plus 4 electrons would give us 2 waters. Okay, that's my 2 half equations. This says write a balanced equation for the overall reaction. Okay, so if we combine those, okay, so if I double this, because remember we need to have 4 electrons, so if I double that, I get an overall equation of okay, even at the moment, and water. Okay, and that's our overall reaction.